So in this short video lecture, we'll be looking at these two concepts, reduced row echelon form and the row echelon form. In order to understand these, we're going to actually have to define some rules and regulations on how or properties that reduced row echelon form matrices have. Essentially, we are talking about the matrices that we've looked at so far, the augmented matrices, and we've looked at an elimination method which leads to the solution of systems of equations. Now, in those, what we have been doing with those matrices is we start with the system, we take the system, convert it to a matrix, an augmented matrix, and then start performing row operations. These elementary row operations are performed till the matrix is reduced as much as possible. So, reduced row echelon form and row echelon form are two forms of reduction of matrices. So let me just go through the properties, how both of these are defined. So the first property, if a row consists of non-zero numbers, then the first of these non-zero numbers is 1. Okay, so let me show you what I mean by that. So here we have any matrix. If a row consists of non-zero numbers, then the first of these non-zero numbers is 1. So if you see what happens in a reduced matrix, usually you would have a situation where you have 1, 0, 0, perhaps 2, and then you have 0, 1, 2, 3, 0, 0, maybe 0, and then a 1. So what this property says is that a matrix is in both reduced or REF or RREF if the first number that you see, and when I say first, we mean always from the left. So we start from the left, okay, from the left to the right. Okay, so that's how so the first, whenever we say the first, we're talking about column 1. We are talking about column 1. So the first column. So we start at the first column, and we move towards the right then. So here, this is your first number. So the first number that you see, 1. The first non-zero number you see, 1. The first non-zero number you see is 1. Now in the same way, if, for instance, here we saw this situation, we would not say this is in neither REF nor is it RREF. Okay, it can be reduced further. So this is neither REF nor RREF. So second property, any rows that consist of zeros only are all grouped at the bottom of the matrix. So let me give you a quick show of that example here. Here's a quick example of, so you see these are here, down here. So you can see that they've been grouped down. So this would be an REF. This would be in REF form. However, or RREF, both. But if I were to change one of these numbers, for instance, this became, for the sake of argument, I changed this to 1, then this is not in RREF at the moment. Zeros should be bunched at the bottom, so we should interchange these rows, for instance. But in its current form, it is not in REF and is not in RREF. Okay, so we have to group a row of zeros, and when we say rows of zeros, we're talking about the left-hand side. We're not talking about the right-hand side. These properties only apply to the left-hand side, not the right-hand side of the equations. Okay. So the next property we have is the position of the leading one in successive rows that are not all zeros is further to the right than the rows above. So what I mean by that is, of course, just a little space here. So what that means is, for instance, if you look at see further right and then further right. Last and final property, and this is the differentiating property. The first three apply to REF. But what differentiates REF and RREF is this final property that every column that contains a leading one has zeros everywhere else in that column. So let's analyze what that means. Let's look at this matrix. So the column with the leading one, what's below it? Zeros. The column with the leading one, above it, below it, zeros. the column with the leading one, above it, all zeros. So this would constitute an RREF. So this one, this matrix is an example of RREF. Okay, so those are the properties that basically define RREF and REF. What I've done is there you can see the summarized all the 4 properties. And remember that, as I said, the first 3, these 3 are for REF, and all 4 give us RREF. So let's look at a couple of examples quickly here, and I'm just going to make up some matrices to show you what these, and then we discover, well, I'll decide whether these are REF or REF. So here, what can we say about this matrix? Is it REF? Well, let's see. First property, if a row consists of non-zero numbers, okay, 1, 1, nothing, so that's okay. First property is done. 2, any rows that consist of zeros only are all grouped at the bottom. Correct? There's only one row of zeros and it is at the bottom. And the third, the position of the leading one in successive rows that are not all zeros is further to the right. Here's the, here's the leading one. The next one is further to the right, and there's no leading one in the last row. So it satisfies the 3 properties. So it certainly is an REF matrix. So it is REF. Okay. Remember, all REF matrices are also all RREF matrices are REF matrices as well. Okay, not the other way around though. Fourth property, every column that contains a leading one. Okay, let's look at this. Is the first column leading one, below it all zeros. Second column leading one, above and below zeros. And then we have third column, no leading ones. Therefore, the fourth property is also satisfied. There's only 2 columns that have leading ones. So this is in RREF, in fact. This is RREF. But let's look at this example. Now, this example, if a row consists of non-zero numbers and the first of these non-zero numbers is 1, 1, 1, and 1. So that's fine. And the next one is there are no zeros, so no need to group them. So that's fine. Third property, position of the leading one's successive rows, not all zeros further to the right. So this one is further to the right and then further to the right. So that's okay. So it's REF for sure. It's definitely REF. So let's write that down here. It's REF. Is it RREF? Well, let's look at it further. The last property says every column with a leading one. This is what leading one, 0, 0. Yes, leading one, 0, but not 0. So this doesn't satisfy property 4. So this is not RREF. It is only REF. So it's REF only, not RREF. Okay, let's look at this example quickly. First property satisfied, second property satisfied, third property there is second property satisfied, there's no group of zeros. Third property, all successive ones are further to the right, 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 and further right. Okay, don't worry about it. It shouldn't be in 1 steps only. This is from here to here. It's further right. This one is further right than this. So we're okay. So it is REF. Is it RREF? No, it is not RREF, because last property says column zeros. Yes. Okay, fine. This is not RREF. This is only REF. Okay, so this is only REF. It is not RREF. I think those are reasonably sufficient examples. Further definitions very quickly. Let's just talk about these 2 elimination methods. Gaussian elimination first. Gaussian elimination is basically bringing the matrix to REF in REF form and then back substituting. Back substitute. That means that you basically write the matrix back in equation form, and then what you get is simpler equations which usually lead to a solution. Let me show you with an example which has already been done. For instance, if we look at this situation, I'm just going to make up the situation here for you. 1, 2, 3, 0, 0, 1, 0, and then we'll say 3 and 1. And let's say we had 1, 1, and 2. So let's look at this example. This is in REF, as we know. This is REF. We all agree it follows the rules of REF. Now what we do is we back substitute. Okay, so back we back sub, which means we write it back in equation form. So the equations will be, and you always start with the last equation first, okay? Last equation first. Now these, we will assume these variables are x1, x2, and x3, so it means that the third equation, x3, is equal to 2. So that immediately gives you the value of x3 actually, which is x3 is equal to 2. The second equation, this one, okay, is going to give us x2 plus 3x3 equals 1. When you substitute the 2 in here for x3, that goes in there. Okay, so that gives you 6, goes to the other side, so that tells us that x2 is minus 5. Okay, so we've got x2 as well. That's 2 of them. Then we go to the last equation, the first one, in fact. So that gives us x1 plus 2x2 plus 3x3 is equal to 1. Substitute in these values, and that tells you that x1 is going to be 1, and then 2 5s is 10, so it will be plus 10, and then 3 2s is 6, so it's minus 6. So it turns out that x1 is going to be 11 minus 6, which is 5. So basically what you have is the full solution of the equations. Now this is called Gaussian elimination. This is called Gaussian elimination, where you eliminate till you reach REF, then you back substitute, and you solve a bit further because you've got a simplified system, and basically you're substituting. If you see, this is also the substitution. So first you write the equation back, and then you start back substituting these numbers. So you substitute them in each of the equations, one to the other, and you know, you basically end up with the solution one after the other. This is called Gaussian elimination, right? And it's named after Carl Friedrich Gauss. I would like you to have a look at Gauss in your own time. Very interesting to read about, an excellent top-class mathematician. Now, the other thing you can do, of course, which we've already done, is that we could do the following, which is 1 0 0 0 1 0. This matrix can be brought to our REF, and in which case we end up with, and we'll most likely end up with this, in fact. And as you see, this is an RREF. Okay, this is RREF, and in this form we get the solution directly. So when we back substitute, rewrite the equations, we get x1 is equal to 5, x2 is equal to minus 5, and x3 is equal to 2. So both, this is called Gauss-Jordan. This one is called Gauss-Jordan elimination. All right, this is called Gauss-Jordan. This one is Gauss-Jordan elimination, and Gaussian elimination I've already shown you. So these are the two elimination methods that I wanted to cover. Now we'll look at quickly how basically we interpret solutions, as in we've already discussed. What I mean by that is, sorry, let me rephrase that. We've seen that there are 3 types of solutions to linear systems of equations. There are unique solution, an infinity of solutions, and infinitely many solutions, and no solution. So how does one recognize which one? Well, this clearly is the unique solution situation, because you've only one solution. Okay, so this is a unique solution. So this is the unique solution that we are familiar with, which is one set of values of x1, x2, and x3. Let's look at an example of what happens, or how do we recognize from these systems what is a no solution or an infinity of solution situation. I want to look at this situation, this particular case where let this number be a. So now I want you to look at this matrix. So what's going on here? We've got what you have to see is that the bottom row is left hand side all zeros, and the right hand side is an a, which I've left as a deliberately. Now here's what I want you to see. If a were 0, okay, if a is 0, we have infinitely many solutions. Okay, infinitely many solutions. Okay. Why? Because when you write the equations, I mean the last equation. So that what we're saying is, then that means that the matrix in this case would be just 1 2 3 0 1 0 0 0 0, and here you have 2 3 and 0. So when you back substitute that, what is the substitution of this equation? It's the 0 equals 0 situation. You remember that? That was the case where we had in the simultaneous equations when we were looking at linear systems of equations. That's a situation where infinite solutions. Okay? What are those infinite solutions? We will do that a little later. Okay? But right now, that's all I'm looking at is how do I interpret, the possibilities, the three scenarios. Now, if A is not equal to 0, I'm saying not equal to 0. If A is not equal to 0, this implies there is no solution. Okay? Why? Let's have a look again. If we look at the same matrix again, and this time I'm going to choose a non-zero value for A. For instance, let's take, for the sake of argument, let's take 0, 0, and here we'll put a 1. Now, when I back substitute, what is that going to look like? It's going to be 0 equals 1. That, if you remember, that is the no solution situation. That there is no solution to the system of equations. So this is very important for you to see that when you come across these two scenarios, you should immediately note that either you have a no solution or an infinity of solutions. If you have a no solution, of course, you stop and say there is no solution, we are done. But if there is an infinity of solutions, the next step is to go and find those solutions. So we have to work on finding those solutions, and that's what we're going to do next. So let's look at the infinitely many solution situation, and what I'm going to do again is here, let's look at the situation of the infinitely many solutions. So again, I'm going to do this by example. But first, I will tell you that the solution of a system is called a general solution. And it's also known as we introduce the concept of parameters. So these are two ideas that you need to keep in mind, and I'll explain what these are as we proceed. So again, I'm going to just create a matrix here, all right, just for you as a quick example of an infinity of solution situation. And here's the infinity solution. So here's a 3x3 system, simple, right? Let's keep it simple. And what we want to do is, this has infinitely many solutions. So it has infinitely many solutions. And the question is, what are those infinite solutions? What are they? So in order to do that, first of all, you need to back substitute. Let us back substitute. And there's nothing that comes from the last row. We get x2 is equal to 3, and we get that x1 plus 2x2 is equal to 2. Okay, so if I put the 3 value in here, this implies, these two imply that x1 is going to be, well, 3 to 6 goes to either side, so it's going to be minus 4. But what is the value of x3? Well, so what we're saying is x3 can be anything, any parameter t. So that means the solution to the system is x1 is minus 4, x2 is 3, and x3 is t. Now you can check. For instance, example, okay, let t equal 1. Okay, if t is 1, now what is the set of equations? Remember, the only equations you have, well, whatever's the original system, I don't have the original system here, but you can use t equals 1, and that means that the solution you have is minus 4. Basically, if I write it as an ordered triple, it'd be minus 4, 3, 1. That's one solution. That's one solution. When t is equal to 2, you get minus 4, 3, and 2. When t is equal to, this is for t equals. So as you see, here is another example of a matrix that has infinitely many solutions. Let us write the equations associated with this matrix. So the first equation is x1 plus 2x2 plus 3x3 plus 4x4 equals 2. And the second equation is x2 plus x3 equal. So just two equations in this particular system of equations. Now you will see that that's all we have. Now the way you start to solve such a system is you see that you have to assume a value for some of the variables. So we'll start by looking at this second equation here. We will assume one of the two, either x2 or x3, assuming a particular value. So we can say that let x3 equal the parameter s. Okay, so this is a parameter. Let me write that down here for you. So s is a parameter. Now, so that means that x3 is equal to x, which implies from this second equation that x2 is equal to 3 minus s. So we've got the value of x2. Remember, s is not an unknown. S is a parameter. It is not a variable. It is a parameter, which means it can be set as a constant. So therefore, x2 is now 3 minus s. So we have got two of the values done. Now, we will have to assume other values. So what we can do here, and it's completely open, we will let x4, for instance, we can let that equal t. So if x4 is equal to t, and we have x2 and we have x3, now we can find x1. So from the first equation, let's say that x1, we have x1 is equal to 2 minus 2 times 3 minus s, that's 2x2, okay, and then minus 3 times s and minus 4 times t. So that's the value of x1. So let's simplify that. So we get 2 minus 6 plus 2s minus 3s minus 4t, and that boils down to 2 minus 6 is minus 4 minus s minus 4t. So our solution, so that's the value of x1. So I'm going to put little squares on these solutions. Okay, so that's x2, that's x3, and that's x4. So we now have all four values. Now, what you can, so actual, these are called, this is a general solution. So this is known as a general, which I mentioned earlier, this term, general solution. This is called a general solution to the system of equations. And now we're looking at a particular solution. Let's look at a particular solution. So particular solution for this problem would be if we choose s equals 0 and t equals 1. And you can choose s and t both to be 0 as well. There's no issue there. So that means that, let's have a look. So what will happen is that x1 will be, actually what I'm going to do is, to make things easy, I'm going to let t be 0 also. So both s and t are 0. If s and t are 0, then x1 is equal to minus 4. Okay. x2 is equal to 3. x3 is equal to 0. And x4 is equal to 0. So there you go. That's one particular solution to this system of equations. But as you can see now, I keep choosing the value of s and t. Any combination doesn't matter. They don't have to be the same. They can be different. S can be 1, t can be 3. They don't have to be the same. And you can see there is, of course, infinite possibilities now for solutions for this system of equations. So this is an example of infinitely many solutions. And the general solution has two parameters, s and t.